Given that overview, let's now look at more detail about how Wi-Fi works. And the objective here is just to give you an understanding so that you'll realize why we're making various recommendations to improve Wi-Fi throughout the building. Now, Wi-Fi is really just a combination of radio transmitters and receivers. The access point, the Wi-Fi access point, has one or more transmitters and one or more receivers, and they transmit a signal over to your laptop, your phone, your tablet, and so forth. And your laptop and those devices also have a transmitter and receiver. Now, in most cases, in all the modern equipment, are dual band. That is, there's a band called the 2.4 gigahertz band, and the second one is the 5 gigahertz band. These are two frequency ranges that are used, and they have different advantages. The 5 gigahertz is the newest, and it allows the fastest, highest performance. However, its distance, its range is reduced compared with the 2.4 gigahertz on older standard, which has a longer range, but its performance is not as great. And one of the unfortunate things about the 2.4 gigahertz is there are a lot of other types of devices that operate in that range and can cause interference. So now let's take a look at how these connections are made. On the one hand, we have our Wi-Fi access point. We're going to call that Joe. And on the other side of the conversation, we're going to have a laptop, and we'll call that Carl. And let's see what goes on between Carl and Joe. Now, of course, this conversation is taking place through radio waves, but we'll imagine that it's something more like an English language conversation. And there's Joe. Joe's out there saying, "Hey, my name's Joe. Here I am." And Carl sees that and asks if he could join the conversation. Joe says, "Yeah, okay, just give me the code." And Carl says, "Yep, here's the code. Let me in." And Joe says, "Okay, you're now part of the conversation. You can continue to converse as you choose." So Carl over here says, "Let's go find the opera schedule," and tells Joe where the address is, and Joe sends that request out to the internet. It comes back really quickly, and Joe says, "Here it is," and Carl says, "Yep, I got it, thank you a bunch." Now, there's a lot of things that go on in this conversation that are really notable. This first one, "Hello, my name is Joe," actually, every Wi-Fi access point sends out a short signal, generally 10 times every second, broadcasting their identity and their capabilities. So, "My name's Joe. I can transmit on these bands. I can transmit this fast," etc. Carl, on the other hand, his laptop, while disconnected from the Wi-Fi, can look around and see that Joe is broadcasting, and perhaps a bunch of other broadcast signals are available. Carl sends that request to join, and when he does so, generally there'll be this secret code that allows an encrypted conversation, such that all the conversation after that point is hidden from prying ears that might want to listen in. Once those connections are made and they've established the connection, normally Carl and Joe can eliminate the requirement to do this manually, and the connection is done automatically. Anytime Carl wants to have a conversation, Carl can just start talking. Now, I suggested here that Carl asked to go find the opera schedule. And let's imagine that Carl is trying to get the opera schedule at the Sydney Opera House down in Australia. I wonder how long it'll take to send a signal down to Australia and back. Well, it turns out the speed of fiber optic communications is incredible. Theoretically, Carl could send that signal and get the reply back 5 times a second. That is about 2/10 of 1 second to go halfway around the world and back. I recently did a test just to see how fast it might actually be, and I came out 3 times a second, which is really, really remarkable in my opinion. Okay, so now let's take a look at the conversation in a little bit more detail. Here's Joe. Joe's got a megaphone, and of course, what we're representing with this megaphone is the transmitter and transmitting antenna that exists in that Wi-Fi access point. Joe sends a signal. Carl's over there listening. He's got some ears. He's got his radio receiver waiting to hear from Joe. And when Joe sends out a signal, Carl hears that and can decode it and take appropriate action. Likewise, Carl has his own transmitter and transmits back to Joe's ears. I'd like you to notice a subtle point here. Joe has a bigger transmitter and bigger ears than Carl does. And the reason for that is that Joe is powered by electrical power through the outlet, whereas Carl is a battery-powered device. And there's always this trade-off with battery-powered devices. You could have them more powerful, have them have better antennas, but to do so in a small space and lightweight is a trade-off. So the point here is that regardless of the capability of transmit and receive that Joe has, the limiting factor in terms of a communications link between Joe and Carl will generally be the capabilities of the mobile device. It won't generally be as fast as the Wi-Fi access point. Let's now take a look at interference. So here we have our basic communications channel, and imagine that you have a loud neighbor. So rather than Joe transmitting by himself over to Carl's ears, this loud neighbor comes in and sends out a transmission also. Now that transmission then can interfere with the signal that Joe's trying to send, and Carl may not be able to understand what's going on here. In the worst case, Carl basically says, "I don't understand," sends a signal back to Joe and says, "I didn't hear you, would you repeat your message?" And in doing that, this interference then can slow down the overall conversation because the requirement to retry once or many times simply slows down the useful conversation dramatically. Now, this type of interference from this loud neighbor is what I would deem Wi-Fi interference. It's someone else on a Wi-Fi channel that's interfering with the desired conversation. There's a second kind of interference, and that comes from other sources, and it falls in out of the blue and can wreak havoc with this conversation, just like the loud neighbor can, and in fact, sometimes much, much worse than that loud neighbor. This kind of interference comes from things like microwave ovens, like certain types of security cameras, and many more devices. We'll take a closer look at those later in the presentation. In order to overcome interference and overcome loud neighbors and so forth, there's a technology called MIMO. It's multi-input, multi-output. Without going into much detail, the basic idea here is to give Joe more than one antenna and to give Carl more than one ear and let them send multiple signals from Joe and into those multiple ears through the magic of signal processing, which is way beyond my expertise. The capability of using these multiple input, multiple output devices improves the distance and reliability and speed sometimes quite dramatically. And just like in the Joe having his 2 megaphones, then Carl may have 2 megaphones also. It turns out that 2 or 3 antennas, 2 or 3 transmission signals and receivers are typical for today's high-end equipment. However, some of the older equipment may well just have 1. Now, so if you do have a Wi-Fi access point like Joe that has 2 or 3 antennas, but you have an old laptop with only 1 ear and 1 antenna, then the limiting factor is going to be that laptop and not that access point that Joe has. We'll transition now to looking at some of the differences between Wi-Fi and wired connections. Imagine that you had a Ethernet cable that you plugged directly into your router and from that into your laptop. You'd be carrying the signals in that conversation across wires rather than across the Wi-Fi radios. In fact, these cables have 4 pairs, twisted pairs of copper cable, and that's what carries the signals in a wired connection. For the Wi-Fi connection, there's the intermediate where you come from your router into the Wi-Fi access point, and then that final link is the Wi-Fi link, shown here in blue. Let's look at some of the comparison between the 2 types of connections. On the one hand, Wi-Fi is a little bit like a bridge, and it's like a 1-lane bridge. A wired connection is more like a 2-lane bridge. In that sense, the signals can traverse down the bridge in one direction and come back in the other direction, and can do so simultaneously. So it's a 2-lane bridge. This allows no slowdown if you're trying to transmit and receive at the same time. On the other hand, the Wi-Fi connection, you really have to take turns on this 1-lane bridge. If our yellow bug is going to go down the road, it's got to get out of the way and finish its crossing the bridge before that BW can come back in the other direction. So this 1-lane bridge right away is an impediment to high performance as compared with a wired connection. The other problem that we see over in Wi-Fi is not only does the traffic cross that bridge not only does the traffic crossing that bridge is represented by these Volkswagens, but other traffic can get on that bridge without permission and get in your way, like a motorcycle, like a big obstruction. A train might cross that bridge, and those things can kind of wreck your day. Whereas over on the wired side, we don't have to worry about intrusions. We can mark our property as private with no trespassing, but the reality is that on the Wi-Fi side, our bridge is open to signals coming in from different locations and interfering with our signals. On that wired side, we're really protected, and nothing can get in and get in the way. Looking some more at the potential connections, imagine that you have a wired cable that's 3 feet or 30 feet or 300 feet long. And we look at its signal strength as with respect to distance. Well, the signal stays its full strength and hence full speed regardless of distance. On the other hand, that Wi-Fi signal traveling through radio waves loses strength. As you move away from the Wi-Fi access point, the signal gets lower and lower, and that's going to occur for both the 2.4 and the 5 gigahertz signals. I mentioned earlier on that the 5 gigahertz signals don't have as much range, so their signal strength drops off faster with distance than the 2.4 gigahertz. Now, as seen in the previous slides, there can be interference with our signals, and that radio signal interference then effectively is if our signals go down below particular strength and get down into the radio interference region, then the conversation simply can't operate properly. You can't hear the signal. You can't transmit once you're down to a very weak signal. The important thing then is the so-called signal-to-noise ratio, which is the distance between the signal strength for radio interference and your actual individual signal strength, as depicted here with the black arrowed lines. When that distance is big enough, you can have a good, strong Wi-Fi conversation, and if that distance gets too small, then the conversation loses its speed and eventually drops off and becomes unusable. Now, this diagram shows just the rough idea of how signal strength may fall off with distance. I actually have some measurements taken in the lobby. The top green line is the signal strength, and the blue line at the bottom is the interference signal. For the first 25% or so of the time from the left, I was standing underneath the Wi-Fi access point in the lobby, and then I slowly walked to the far end of the lobby, and you can see the signal strength dropping off as I was moving away. Still, throughout this space, the distance or the difference between the signal strength and the noise or interference signal is quite large. So throughout that space, we would expect to have very good Wi-Fi performance. Let's go back to the previous slide then and take a look at one of the realities in the Wi-Fi space, and that is that unlike the lobby where things are all wide open, we're really having to deal with obstructions, walls within our condos. And when the Wi-Fi signal goes through the various walls and bookcases and refrigerators and what have you in our space, the signal strength drops off even more rapidly. As indicated here, the 2.4 gigahertz channels don't drop off that much. The walls and other obstructions do drop off more severely with the 5 gigahertz. That is, the 5 gigahertz does not penetrate walls and other material very well. On the wired side, however, assuming that you can drill a hole through that wall, you don't lose anything with distance. Now, there's various types of walls. If you think about it. Within your condo, you have a neighboring condo, and walls in that case are good. The walls between you and your neighbor, as far as Wi-Fi is concerned, is really good because you'd like to block your signal from getting out and their signal from getting in. On the other hand, walls within your space are bad because you don't want your signal to be dropped off between, say, your bedroom where your Wi-Fi access point is and the living room where your television is. So we have good walls and bad walls. And by the way, think about the ceilings and floors, also these thick concrete spaces. Those are good, but signals still do penetrate them for sure. Now, I've mentioned the noise, and I'll define this now as background noise. It's kind of there, it's everywhere, it's a minimal amount of interference that exists no matter where you go within this building, or really if you go out away from this building. Now, in addition to the background noise, there's something that I'll call local noise, and that's noise or interference that's being generated inside your condo and in your neighbor's condo. So if the background noise gets very large, then we find that the Wi-Fi signal may be too weak to properly communicate. And so what are the options that we have if we've got local noise that's being generated nearby? Well, really three things you can do. You can have a stronger signal, that is, try to increase the power of that Wi-Fi signal. You can eliminate the noise, or you can have an improved radio receiver, improved equipment that can handle dealing with the noise environment. If we choose to make a stronger signal, we increase the height here from around 100 to say 130 in some arbitrary units. Then our signal is higher than the local noise, and looks like that would be a good solution. However, imagine if everybody does that. If everybody does that, turns up their volume higher, then it actually generates more local noise, and it's a losing situation. So the idea of going with a stronger signal, that is more powerful radio transmitters, simply doesn't work in a high density environment. It's counterproductive. All of you have experienced this in a different way. Imagine you're in a restaurant, you're in your favorite red table and having a nice conversation with your friends. And as the evening goes on, the restaurant gets a little more crowded, so more people come in, this wedding party, a couple of folks over at the bar, they're having a really good time. And after a while, you find out there's just more of a roar. The whole place is just filled with noise, with conversations, and you can't carry on a good conversation. So imagine this space where there's a blue and violet and yellow and red and green and purple conversations going on, and you're just overwhelmed. You can barely talk to the person next to you. So we're in this really nice restaurant, and you say, well, what can we do? This is terrible. You pull out your American Express Platinum card, go over to the maitre d' and say, hey, would you fix this? We're trying to have a conversation and it's not working. And the maitre d' says, got it, I'm on it. Maitre d' goes in and he decides that he'll have each table operate in such a way and have a conversation that isolates them from their neighbors. So you're here having your red conversation and you're in the red zone, and your immediate neighbors are having conversations in blue. So imagine you're speaking English, and for the moment, the blue is perhaps Japanese and green is German. And imagine that you don't even hear that Japanese or German conversation, just the English. You're isolated. And so that's the kind of thing that we want to do in the Wi-Fi space, is have an allocation of languages, of radio channels, such that we don't interfere with our nearby neighbors and we can all have a nice, quiet conversation. Now, as far as radio channels are concerned, in the 2.4 gigahertz space, there are nominally 11 channels available for use. However, only 3 of them are useful, and we'll show you about that in a moment. In the 5 gigahertz space, there are 8 unrestricted channels, but really there's 2 groups, 2 wide channels, 2 groups of 4 that in fact are most useful to us. Now, those channels for 2.4, if we have 11 channels, it's very much like this highway. There's 11 lanes of highway, and you would think that would be absolutely plenty in terms of Wi-Fi channels to distribute them throughout, such that you weren't on the same channel as your nearest neighbors. However, unfortunately, Wi-Fi signals really take up more than one channel, and they take up 5 channels. In this case, channels 4, 5, 6, 7, and 8, even though that Wi-Fi signal is nominally on channel 6. It takes up a whole bunch of the road, so those 11 lanes of traffic are really reduced significantly. And we look at the other 2 sides, we really have room for 3 lanes of traffic, 3 Wi-Fi channels that don't interfere with each other. If that car that was originally on channel 6 decides to move over to channel 5, it's going to bump into the car that's on channel 1, and we're going to have a crash. So the message there is there are only 3 usable channels that don't overlap, 1, 6, and 11, and every Wi-Fi arrangement that you see in professional buildings where there's one company that's doing the entire Wi-Fi system always uses just those 3 channels to avoid the overlap. For the 5 gigahertz channels, we have channel ranges 36 through 48, but effectively there are 4 channels. And in that case, what we've chosen to do and what the general approach is these days in many environments is to have one car take up 4 channels. And by doing that, effectively you're giving them the entire road for themselves. They can go really fast. And there's enough space to do that. And this is effectively the way we've set up the Wi-Fi within the spires. So we've allocated 4 channels for one of the 5 gigahertz bands, and then another 4 channels for the other one. And that's the allocation that we have here at the spires, and it maximizes performance and minimizes interference. Now that you've got kind of an overview of Wi-Fi signals and how they relate to the real world here in terms of a non-technical view that is a highway, let's look at some results